back to the next segment on in situ chemical oxidation. In this segment, I'll be speaking about aquifer material interactions. What is this? It's the unwanted oxidant consumption by the natural organic matter and other reductants present in the aquifer material and the associated groundwater, such things as organic carbon and reduced minerals containing sulfur, manganese, and iron. So if we stare at the pore scale conceptual model and we flush oxidant through this pore scale model, the oxidant, it will try to oxidize any reduced species present. And they might include pyrite, manganite, charcoal, and feldspar, or napple. That's really what we wanted to treat, but the oxidant doesn't know that, and it's a very competitive process, and it will oxidize that with the highest reaction rate. Now, what does that mean? Well, it will increase the consumption of the oxidant through unproductive reactions. It will increase the auto-decomposition rate. It will decrease the ability of the oxidant to be transported away. It will decrease the overall reaction rate between the oxidant and the compound of concern, and will decrease the amount of oxidant mass available in the entire system. By and large, it creates a very inefficient treatment system. So what we did is we ran some experiments on peroxide, permanganate, and persulfate to see how those three primary oxidants interact with 10 aquifer materials collected from various locations around North America. We see for peroxide, again, peroxide, just H2O2 mixed in with the aquifer material, and observe the rate that the peroxide will auto-decompose over time. So one can quickly see here that for certain aquifer materials, the presence of a reduced species caused the reaction rate or the auto-decomposition rate to increase over time. So if you plotted then the rates of these 10 aquifer materials versus the observed rate of reaction and computed those in terms of half-life, you can see quickly that the half-life can span between a couple of hours to close to 20 hours. So there's quite a range of stability, if you will, of peroxide within an aquifer material itself. Well, for permanganate, it's not quite the same. So in the case of peroxide, I spoke about an enhanced auto-decomposition rate. For permanganate, we use the term natural oxidant demand, and that is essentially the mass of permanganate consumed per kilogram of solids. So it's actually a consumption, and once the demand is met, there is no more consumption, unlike the behavior of peroxide. So if you ran a batch test, put in a known amount of permanganate into a reactor, add in a known amount of mass of dried aquifer material, the data that you would generate from an experiment like this would be the NOD versus time, and it would show you an increasing rate at early time to a plateau. So again, early time at very high rate, to a longer term or slower rate, to a plateau that I've called the NOD max, or the maximum natural oxidant demand for that particular aquifer material. It's surprising, though, that if you repeat these test for a range of mass. So the concentration now of permanganate is the same at 10 grams per liter, but increase the mass. You can see that as you increase the mass, the NOD max gets smaller. So in fact, the experimental design can dictate what type of NOD behavior occurs. So what is the importance of permanganate NOD on cost? So if you did a calculation here of the amount of permanganate required to oxidize completely 2% of pore space occupied by PCE, added that onto a aquifer material that had 5 grams per kilogram of NOD, then you would be staring at a percent of the demand, of the total demand, that is the demand to oxidize all of the PCE plus the demand to meet the natural oxygen demand of the aquifer solids itself. That would be a line that would go from 2 up to around here, and this simple plot says that 40% of the demand would be going to satisfy the natural oxygen demand. That is, 40% of the cost goes to an unproductive consumption of the oxygen. If we stare at some flow-through column experiments, you can see the behavior in the breakthrough between a tracer curve and permanganate curve. You see a fast reaction will delay the behavior, and a slow that will cause a long asymptotic tail. For persulfate, it behaves in a very similar case to peroxide, insofar as the behavior of persulfate in the presence of aquifer materials shows that the aquifer materials will enhance the degradation rate. Here's a plot for persulfate at a concentration of 1 gram per liter for 2 aquifer materials. Here's what we get for the spectrum of those 10 aquifer materials, and you can see the half-life will range between 16 days and 174 days, really clearly telling us that persulfate in the presence of these aquifer materials, unlike peroxide, is much more stable. So we see that for peroxide and for persulfate, they result in an enhanced decomposition rate. And for permanganate, there was a finite demand that was proportional to how much of the TRC stands for the total reductive capacity of the aquifer material. Let's inject in peroxide, persulfate, and permanganate into an aquifer, which has no flow and no diffusion at all. Let's inject in these 3 oxidants now at the same oxidation strength. So I've changed the injection concentration here, so I've got them to be in terms of their equivalency to be the same. I'm going to inject them on at day 0, and then 30 days after that, I'll re-inject into the same aquifer. So what I've got here on the screen is the profile of peroxide. So you see that it's the same profile at day 0 and day 30, and you can see very quickly that for the aquifer material that I used here, that's not very stable, and it's not around that long. Here's the profile for the permanganate ion. After the first injection, not all of the NOD is consumed, but some of it is. So the second injection at day 30 shows that the profile is not the same. So some of the NRD or some of the interactions now are lessened because that aquifer material has already seen that oxidant. And for persulfate, it behaves in, as I said, in a very similar fashion to peroxide, and the behavior remains unchanged between injection episodes. So that concludes this segment on aquifer material interactions. And the next segment, I'll be speaking about some early lab results and this concept I call enhanced mass removal. That's all for now. Talk to you later.